Giri with Alstom. I'm a bit of an outsider here. I'm not part of the inner B-Circ circle, or not a graduate of Virginia Tech or a graduate of Cornell, but nevertheless I've benefited a lot and interacted with Arun and Jim quite a bit. I've had the privilege of working with Arun at University of Wisconsin-Madison with Bill Long on the smart grid operations course, and I think I learned more by having him participate. And also we've been working with Jim Thorp on some projects, trying to get him engaged and so. But I have been interacting with them significantly during the IEEE meetings and other activities. And one thing which really struck me was how humble and unassuming they are. I mean, considering all the vast achievements that they've accomplished, that they really are very humble people, and that's something which was very inspiring to me. One story I do want to tell is we were trying to engage Jim as a contractor for one of our R&D project proposals, and we had a French tendering manager putting it together. So he got Jim's resume, and then he asked Jim, saying, "Could you please send me your references?" And he copied Manu and me. So I told Manu his reference is the Benjamin Franklin Award. So that's, but what he really meant was a list of papers. What have you done? So it was a language issue, which but in any case. I'm from the EMS, the dark side. I mean, I'm on the system side. So we deal with the big picture, the complex engineering machine, which works 7 by 24 remarkably, 99.9% of the time. And I've been in that business ever since I graduated from college in upstate New York. And what we're seeing right now is really what I would call a tantalizing change with synchrophasors of how EMS is going to change in the future. I mean, for the past 30 years, we've been running the EMS with scalar measurements every 2 to 4 seconds, and basically monitoring the quasi-steady state behavior of the grid. But now with all the renewables, demand response, and power electronics loads, you're introducing a lot more instability type issues and oscillations and harmonics, so stability and dynamic stability becomes more important. So I think with synchrophasors, now we can start looking at the grid with a much finer microscope of looking at the stability of the grid. And the other thing which I see in the EMS side is we've never had a synchronized view of grid conditions, meaning time synchronized. And for the first time, we're going to have the opportunity to look at grid conditions in a time synchronized manner across the grid. So the time synchronized view of the grid plus the stability issues, monitoring stability, and looking at early warning signals is really how it's dramatically changing how the EMS of the future is going to be and how it's going to help us deal with some of the new challenges. So I just want to sort of say a few words before Manu gives a more detailed presentation. But one thing which we did last year with Manu's help was have our team members put together. Our company has an internal innovation award. So they solicit inputs from around the globe, and they receive hundreds of applications for what people feel are their innovation contributions to our company. So our team put together proposals related to integrating synchrophasor analytics with EMS and visualization. And lo and behold, we won the gold medal and the first prize, and Manu and team went to Paris, all expenses paid, thanks to synchrophasors, and chips. So I think it was very, so it shows that the EMS is at a precipice right now of really benefiting from synchrophasors. But they have to grow in numbers. It's not just having a few. We need to have them at least across the grid at all the high voltage substations, etc. So really, I mean, it's re-energized the EMS business in that sense, because it's providing new opportunities to provide tools to what Wahid was saying is what we need to provide to the operators. And so with that, so just a quick introduction. I just wanted to then hand it off to Manu, who's going to go through maybe a little more details of some of the solutions.
Thanks, Jay. Well, good morning, everyone. As I said last night, it's been a very big privilege to have Professor Thorp as a mentor and interact with Professor Phadke. And it's been exciting working in this area, working in the area of synchrophasors. I owe a lot to these two people, including, as Jay mentioned, my most recent trip to Paris and the Innovation Award that we won. So what I'd like to talk about is how synchrophasors are changing the landscape in the EMS industry. And if you look back and look at how the EMS industry has evolved, there are very few revolutions. There are quite a few evolutions, but very few revolutions in the EMS industry, and they are approximately 20 years apart. So if you go back to the 60s and 70s, we had analog systems. These were centralized systems. We started getting SCADA measurements, voltages, flows, status information, and the first truly wide area control scheme was implemented, the frequency control, which is AGC. So those were very simple EMS systems back in the 60s and the 70s. And then after computers, that revolutionized the industry, and what we could do is take those measurements and combine them with the model and add predictive capabilities. And that's where the state estimator and the contingency analysis came in, taking the model, estimating the state, and being able to predict. Late 90s, deregulation, and markets came into play, and they added their own challenges. And now, 20 years later, we have synchrophasors. And as Jay mentioned, what that's providing us with is dynamic observability into an otherwise steady state way in which we operate at the grid. Phil showed you the slide earlier. This slide came from M.S.E.E. You know, if you look at the deployment of PMUs in North America, it took 20 years to install the first 200 PMUs. And most of these were R&D grade PMUs. And if you look at the last 3 years, that number, by Phil's estimate, has grown more than 6 times to around 1,200 PMUs. The point I'm making here is synchrophasors are becoming an integral part of the way we monitor the power system and an integral part of the energy management systems. So, when I joined Alstom a few years ago, one of the main reasons why I joined Alstom was Jay's vision of combining measurement-based and model-based solutions, bringing in synchrophasor information to complement the model-based solutions in the EMS. It was interesting, last year we participated in a couple of DOE projects, and the very same theme was the topic, which was measurement-based and simulation-based systems. Okay? And this realization of combining measurement-based and model-based solutions is something that we have been after, and for two very important reasons. The first is a comfort level. Operators in control rooms are comfortable with EMS systems. Recently at M.S.E.E, I went out for dinner with a couple of our customers, and they were telling us that they're bringing in the PMU data in there. And now that they have 2 voltage measurements, and they're seeing a discrepancy between those measurements, you want to take a guess which one they trust? It's the SCADA measurement, not the PMU measurement. They're comfortable with it. Another customer, we were trying to, or encouraging them to bring in PMU data to improve their state estimator. And what they asked us to do was, well, first we'd like to see the PMU data alongside our state estimator results without integrating it into the state estimator so that we have confidence in this. right? So if you're familiar with one technology, it makes sense to, when you're adopting another technology, to bring it in the context of the technology you're familiar with. And it's the right thing to do. And synchrophasors complement EMS functions, okay? With PMUs, we can now observe dynamics in the system, but if you want to add predictive capabilities, we need the model. If you want to figure out corrective actions, we need the model. And so there's a synergistic relationship between synchrophasor measurement-based solutions and model-based solutions. And that's the premise of the next generation EMS. So just to illustrate that marriage between the two, with synchrophasors now we can observe dynamics, but we need to bring a context to these observations, and that's where the model-based solutions come in. They tell you where is the edge. So if you're looking at oscillations, we can observe our damping levels, but if you want to know how those damping levels are going to change if you have a contingency, or what do you do to improve your damping in your system, you rely on the models. So a combination of measurement-based and model-based solution gives you a more realistic or more holistic solution to stability. Where is the edge? And that's really what we are deploying in a lot of the synchrophasor SGIG projects. We have the traditional EMS system at the bottom, RTUs, feeding SCADA, feeding the model-based applications, contingency analysis, state estimator. We work closely with Power Tech Labs, and so we are running their stability assessment tools in real time. But then we have a complementary set of measurement-based solutions that rely on synchrophasors, and they convert the high-resolution data into information, and it's the information that we bring into the EMS. The EMS was never designed to deal with data 30 or 60 times a second, but the information that we extract out of the data is what we bring into the EMS to complement each other. And this is something we're doing with Pacific Gas and Electric, we're doing it with BEC. PG&E is perhaps one of our flagship projects, where we are combining the PMU-based applications, as you see down there, with the EMS applications. You've seen some of these displays. This is eTerravision, and we're looking at voltage contours. And the reality is that this is in the control room. That's the PG&E control room, and we have deployed these solutions in the control room at PG&E. You may recognize this person right here. This is Wahid at his POC facility. It really is a state-of-the-art facility. I mean, it's an end-to-end setup from your RTDS creating simulations, dynamic simulations. You have your PMUs, your substation PDCs, you have the communications, a redundant system, the application, all of that in one location, so you can test different aspects of this technology, the standards, the applications, the communication aspects of it. We have learned a great deal working with Wahid and working at the POC. And firewalls, absolutely.
Did you see the toys and the hearings?
Okay, and if you think about control room applications, you're thinking about situational awareness. Providing a complete solution to the operator. Is there a problem? Where is the problem? What do I do about it? And situational awareness to us is a combination of several things. It's wide area visibility, and PMUs play an important role there. But it's also combining it with steady state analysis, like state estimator and contingency analysis, dynamic stability analysis, and this is using the dynamic models and doing a comprehensive security assessment, and non-electrical information, weather data, lightning data, bringing that all together and presenting it such that it tells a story. Again, is there a problem? Where is the problem? And what do I do about it? Here's one of our displays where we are bringing in the PMU data, where he talked about looking at angle differences, relative angles, alerts, disturbances that are detected by the PMU data, bringing it alongside the other information that we're getting from the EMS. Now, oscillatory stability has been perhaps one of the poster child applications for synchrophasors, because you can observe this dynamics, which you couldn't do with SCADA. But the reality is that we need to use it to solve a real problem. And so what we've done in the UK, what we've done in Australia, is actually use it to relieve congestion across corridors. And in both cases, this is a coincidence, but we have tapped into about 300 megawatts of latent capacity, okay, across those corridors. And that's because we've combined the measurement-based solutions and the model-based solutions. With the measurements, we have been able to quantify the amount of conservatism that was there in the planning studies and actually pushed the edge of that limit. Damir talked about using PMUs in distribution, and we're doing that in Scotland, okay? And we're doing it to decide when to connect wind farms. The classic approach of fit and forget is really conservative. And the nice thing about distribution is we're talking about radial systems, and so having just two PMUs, one at the connection point and one at the bit generator, we can say something about the capacity between the two. We can say something about the impedance change between the two. We can say something about the flows, purely looking at the angles. And using the angular separation, we can decide when we can push more renewables through there. Here's another application of using synchrophasors in distribution, and that's fault location. And the idea here is, by having just one PMU and looking at the impedance, we can figure out through different feeders, we can look at, well, what's the candidate locations where you have a fault in the system. And then by a second PMU somewhere else in the system, we can hone in on the exact location from those candidate locations. The holy grail for this technology is wide area protection and control, right? And so we are doing this with Iceland, my colleagues at Scimetrics, and the Icelandic system is quite simple. I mean, it's a radial system. There's a lot of generation on one side, and there's a load on the other side. And the scheme that we've implemented there is one where if you have loss of large load, the frequency changes naturally, and the frequency change here on the left is much faster than the frequency change on the right, creating a large angular separation, but that's temporary. And so by wide area monitoring, we know whether it's truly an out-of-step condition or it's one where you've lost smelter load here, and then we decide to trip generation accordingly in the system. So by taking measurements across the grid, we are preventing instability in the system. Islanding, resynchronization, and black start, again, because of the angle information, because of the frequency information, it's very easy to detect an islanding condition. And what I'd like to do is show you a short video which illustrates how easy it is to visualize an islanding condition and help with the synchronization process. Sandeep, if you could please. Just minimize the PowerPoint presentation and the video should be, it's all the way on the right, the last, in the lower corner, right there, yes. Yeah, go ahead.
Is it silent or did it have voice?
That's fine. So this is a mini-VEC system. We use it to simulate the Western system. And in this particular application called Phasor Point, we are bringing in those simulated data. And the fact that everything is green is telling you everything's normal. What we are going to do in this situation is open the tie lines to Canada and see what happens. So there's a system disturbance when we open the lines. And shortly thereafter, we can see the angles in Canada lose synchronism with the rest of the system. A very simple visualization, but a very powerful visualization. And the application then allows you to monitor the angular separation across the two islands, the frequency, and the voltages, so that you know when to enable your sync check relays and resynchronize the island. Thanks, Sandeep. Let's go back to the last slide. So, in conclusion, the reality is synchrophasors are here to stay. We have heard about 1,200 synchrophasors, and the number is growing. And it is truly the new heartbeat of the next generation EMS. We're moving away from a steady state view to a dynamic view. Thank you.